Welcome to the CIRPE Global Web Conference. It is such a pleasure being here and presenting my work. I'm Sumit Singh and I'm a PhD student at Cranfield University, UK, working in collaboration with Airbus in the area of digital twin research. Today, I will be presenting my paper on topic towards information management framework for digital twin in aircraft manufacturing. As per today's agenda, I will start with the introduction of digital twin and information management in aircraft manufacturing industry. Further, I'll be talking about how these topics are linked. Secondly, I will explain the digital twin information management framework proposed in the paper. Further, the case study that has been formalized to explore the potential application and the opportunities around the framework. And at last, I will conclude the presentation with the key takeaways and the future work. Digital twin is known by so many definitions. The current demand of digital twin is increasing rapidly both in academic research and in the industry. It is known by many definitions and the keywords such as virtual replication, digital shadow, or virtual representation of a physical asset. Hence, it would be fair to call it as an imitation of the real world product or process in which associated models are integrated to provide useful insights using the data and information. Digital twin has three essential components. First, the physical product in the real space, a virtual product in the virtual space, and the end-to-end integration of the data and information that ties these two spaces together. And the integration of information is the key focus of my research. So information management is no more just a support function, especially in aircraft manufacturing industry. A closer integration of data applications, information services is required along the aircraft life cycle. Today, industries are investing a lot to close the feedback loop of information and insights to enhance the existing product performance and developing new and improved systems based on the learnings along the life cycle. In this process, the information management plays the key role. Digital twin services can be leveraged at different stages of the aircraft life cycle. For example, digital twin for fatigue and damage tolerance to improve existing airframes design, or digital twin application for shop floor production and planning to increase the learning at the manufacturing stage, or digital twin based on when the aircraft is operated. For all these digital twin services to be equally integrated in the existing process, specific information roadmaps and approaches are required. Such approaches will help in the integration of existing tools and the applications dedicated to the individual digital twin or combination of multiple twins. As information is the key for digital twin, such approaches are essential to manage this information. The current paper highlights some of the key challenges in scope of information management for digital twin. The challenges related to the big data, variety and volume is a big challenge as the amount of data generated along the aircraft life cycle is so immense and hard to manage. Information sharing is still a challenge due to the silo effect. How to store and organize information in the best possible way across digital twin tools and applications. A robust information management framework is required to address scalability issues due to different architectures, data load, supply chain complexities, and computational capabilities. If we look at the classic example of asset management, the current state of the asset management, irrespective of any industry, for getting valuable insight from the asset data, there are multiple constraints in the process exerted by the different systems. All these systems have their own integration challenges driven by the complexity of analysis with respect to views required by the user. For the development of digital twin, how to identify and manage these constraints is a big question. The information flow across the digital twin is divided among the three different layers. The physical layer denotes the physical entities of digital twin such as asset itself, at which the data from the real asset is collected in form of sensor data, configuration information for traceability along the life cycle. Information from the physical layer transfers to the data layer. The data layer denotes the data fits for the analysis and knowledge repositories. The knowledge repositories hold business rules, logics, and historical information about the asset. Further, such active data and the knowledge repositories are used by the model layer. The model layer holds the model along the life cycle, behavior model and the logical models for reasoning and giving actionable insights by predicting failures and assessing the current state of the asset. The information generated in the model layer is stored back to the knowledge repository in the data layer. Such information contains analysis reports and recommendations that need to be used for the next digital twin analysis cycle. Information management for digital twin in aircraft manufacturing industry requires a holistic approach to information. As we know, digital twin has the capability to support the transformation of from the data to knowledge. Digital twin is the integration of models along the product lifecycle, using the data in the real time to provide valuable information about asset behavior, and such information retains as a knowledge for long-term system sustainment and usage. Therefore, the information management requires a more holistic approach around data, information, and knowledge. We have defined the phases of information management for digital twin among four different layers. Information identification focuses on identifying essential requirements for digital twin development and sustainment. It covers minimum information required to develop digital twin to resolve big data complexities. Along with the information identification, understanding the information processing and how it is stored or organized is also a part of information management landscape by focusing on data structuring and modeling data for digital twin. Extraction and representation of the useful information for digital twin is the purpose of the third information management phase. The core activities to support this phase include data analytics and data visualization. Information retrieval and retention. This phase involves activities for information maintainability and retrieval along the digital twin lifecycle. Maintainability of information is an important aspect for digital twin use in the long term. As digital twin solution may be implemented, the changes in the requirement along the project lifecycle are common. Therefore, for long run, it is important to maintain the information which is subjected to long-term application and retention. On continuous engagement with the industry experts from aerospace information management and engineering domain, some of the functional requirements are captured among these views based on which the framework is conceptualized. So looking at the first requirement, minimum information means access to the minimum level of information for digital twin development, such as data types, data views. The critical requirements at the physical layer means the identification and access to the requirements based on the digital twin essential components, such as product identification, digital twin models, information management, etc. Different data views highlight the different data views and defining the requirement for each view. The dynamic requirement denotes the access to the changes in requirements for digital twin development with respect to changes in the scale of application. The level of configuration information enables the access to the minimum level of configuration information required for a specific business case. Data mapping covers mapping the different types of data to the digital twin ontology model, either based on the standards or it can be case driven. And fidelity of the system means access to the minimum dataset knowledge for its digital twin to ensure the fidelity of the system is retained. The framework is conceptualized in four different layers. The framework is applicable to the different systems level in aircraft system hierarchy. The physical layer focuses on in capturing requirements for digital twin in form of a knowledge. Ontologies are one of the ways of retaining such knowledge. Second layer focuses on modeling the communication in the process of capturing data from the different systems of our digital twin, enabling flexible data and information architectures. The third layer is dedicated to the identification and mapping, the integration of different models to be used for analysis in the digital twin. Physical model along the life cycle such as CAD, BOM, behavior models and the reasoning models linked to design validation and service concept to extract the current state of the asset. The fourth layer focuses on modeling data for digital twin by specifically looking at the minimum data structure for digital twin data model. As this schematics is closed with a continuous update to show each time there is a change in the requirements for digital twin, what would be the effect on its data model. Each time information is exchanged between different layers, a workflow is created. At an enterprise level, multiple workflow already exist within the business process. The integration of the existing workflows become essential along with the information management activities around digital twin. For the potential application and the benefits of the framework, a damage tolerance in an aircraft wing is formalized as a case study. Fatigue crack growth and propagation is a classic problem within the aircraft structures. The physical layer is identifying the existing requirements of the system, which are captured in the form of requirement model. Ontology is one of the dynamic ways of semantically capturing and maintaining requirements as a form of knowledge. In the data acquisition layer, sensor data is collected for the number of fatigue cycles and strain measurements using smart IoT solutions. The model layer is where the data is transformed into valuable information and actionable insights. Model along the life cycle, such as the digital mockup, is widely used in the industry. A behavior model for the fatigue crack calculation developed during design and testing phase of the wing structure is calculated. Reasoning model covers knowledge related to the design and testing threshold parameters. Such parameters include additional knowledge from the service and the maintenance on the ground, which would also enable digital twin to match the existing crack growth to the initial design and the testing specifications. All these models need to be integrated with continuously updated along the digital twin lifecycle. Data model is where the data is further structured and stored in the digital twin. Digital twin ontology model acts as a guide to divide the data from acquisition layer and result from the model layer among the different classes. Such division leads to an optimized data structure for digital twin data model. The data model structure will enable different actors to develop application specific to digital twin interfaces and dashboards. The associated workflow defines the necessary task while applying the framework across the enterprise. To conclude, one of the key highlights of the paper is the role of information management and how information management play a significant role in leveraging the digital twin up to its full potential. As data and information is the primary key to enable digital twin, a deeper integration of information management is required. The paper discusses the concepts such as digital twin information flow, digital twin information management phases, and digital twin functional requirements in aerospace industry, on the basis of which the existing framework is proposed. Start with the physical layer from capturing requirements to modeling data for digital twin and the continuous updation along the digital twin lifecycle. The framework has a potential of serving multiple use cases along the aircraft lifecycle. The framework will act as a single information architecture in which users can design and develop their digital twin and manage data and information more effectively by building and maintaining knowledge along the digital twin lifecycle. So far, the current approach is applied to one case study, but testing the robustness of the framework with multidisciplinary case study is seen as the next step, and qualifying or quantifying its benefit over the existing approaches as a future work. Thank you very much for your attention. I would like to take this as an opportunity to acknowledge and thank Airbus and APSRC for funding this research. And finally, many thanks to the CIRPE organizers for accepting the paper and giving me the opportunity to present my work. Thank you.